All right, folks, let's dive into the world of statistical inference and hypothesis testing. It might sound a bit dry at first, but trust me, it's fascinating stuff once you get the hang of it. Let's get started with something called statistical inference. Now, what is statistical inference, you ask? Well, it's all about making judgments about a larger group or population based on a smaller sample. Think of it as trying to understand a whole pizza just by looking at a slice. Makes sense, right? One key part of this process is called hypothesis testing. Any guesses on what a hypothesis is? A hypothesis is essentially a statement about one or more populations. For instance, we might hypothesize that the average return on a certain investment is 5%. Hypothesis testing helps us objectively determine whether the sample data supports this hypothesis or not. In the finance world, making informed decisions is crucial. Whether you're an analyst, an investor, or a financial advisor, you need to base your decisions on solid evidence. Hypothesis testing provides a structured way to make these decisions by assessing whether your assumptions, hypotheses, about the financial world hold true based on sample data. It's like having a scientific method for your financial analysis. In finance, statistical inference involves two main things: hypothesis testing and estimation. Hypothesis testing is where we make statements about a population using a sample, while estimation is about guessing the value of population parameters based on sample data. And guess what? We can make point estimates or interval estimates. Fancy, huh? Let's walk through the steps involved in hypothesis testing, and I'll explain each one with a bit of a friendly touch. First, we need to state our hypotheses. This involves formulating the null hypothesis and the alternative hypothesis. The null hypothesis is like the default assumption, something we assume to be true until proven otherwise. The alternative hypothesis is what you might think of as the challenger. It's what we suspect might be true instead. For example, if our null hypothesis is that the average return on a stock is 5%, then our alternative hypothesis is that the average return on a stock is not 5%. The null hypothesis always includes an equality, for example, equals less than or equal to, or greater than or equal to. While the alternative hypothesis includes an inequality, for example, not equal, greater than, or less than. Next, we figure out the right test statistic and its probability distribution. This is like choosing the right tool for the job. The test statistic is a value calculated from our sample data, and it helps us determine whether to reject the null hypothesis. The choice of test statistic depends on the nature of the hypothesis and the type of data we have. Common test statistics include the z-statistic and the t-statistic. The z-statistic is used when the population variance is known, while the t-statistic is used when the population variance is unknown and the sample size is small. Then we decide on our significance level. This is like setting the bar for how sure we need to be before we reject the null hypothesis. The significance level, often denoted by alpha, is the probability of rejecting the null hypothesis when it is actually true. Common choices are 5% or 1%. This step is like setting the stakes of our game. How strict do we want to be? A lower significance level means we're being more stringent about rejecting the null hypothesis. For instance, a 1% significance level means we're only willing to accept a 1% chance of mistakenly rejecting the null hypothesis when it's true. We also need a decision rule, which tells us when to reject the null hypothesis. Think of it as our game plan. This involves identifying the critical region and critical values. The critical region is the set of all values of the test statistic that lead us to reject the null hypothesis. If our calculated test statistic falls into this region, we reject the null hypothesis. The decision rule is based on the chosen significance level and the distribution of the test statistic. For example, if we're conducting a two-tailed test at a 5% significance level, we would reject the null hypothesis if our test statistic falls in either the upper 2.5% or the lower 2.5% of the distribution. We gather our sample data and calculate the test statistic. It's important that our data is free from errors and biases. This step is pretty straightforward. It's all about doing the math correctly. For example, if we're testing the mean return of a stock, we would collect a sample of return data, calculate the sample mean, and then use the appropriate formula to compute the test statistic. For example, a z-score or t-score. Now, we compare the calculated test statistic to our decision rule and see if it falls within the acceptance region. We compare the calculated test statistic to the critical values and determine whether to reject the null hypothesis. If our test statistic falls within the critical region, we reject the null hypothesis. If not, we fail to reject it. This step is where we see whether our sample data provides enough evidence to support our alternative hypothesis. It's like a courtroom verdict based on the evidence. Do we have enough to reject the null hypothesis? Finally, we make our economic or investment decision based on whether the hypothesized values are statistically significant and economically meaningful. For instance, if we reject the null hypothesis that the average return on a stock is 5%, we might conclude that the stock's actual return is different from 5%. But what does this mean for our investment strategy? We need to consider whether this difference is economically significant and how it impacts our decisions. Let's look at an example to make things clearer. Suppose we hypothesize that the population mean risk premium for Canadian equities is less than or equal to 0. The null hypothesis is that the population mean risk premium is less than or equal to 0, and the alternative hypothesis is that it's greater than 0. This sets us up for either a two-sided or one-sided hypothesis test, depending on what we're looking for. A two-sided test looks for any significant difference, while a one-sided test looks for a difference in a specific direction. It's like checking if your coffee is too hot or too cold, two-sided, versus just checking if it's too hot, one-sided. The null hypothesis always includes an equality, while the alternative hypothesis includes an inequality. We can also have two-sided hypotheses, where we test if the population parameter is simply not equal to a certain value. For instance, if our null hypothesis is that the average return on a stock is 5%, and our alternative hypothesis would be the average return on a stock is not 5%. In this case, we're testing whether the return is different from 5% in either direction, higher or lower. Remember, the null hypothesis is what we hope to reject, and the alternative hypothesis is what we're hoping for. One-sided hypotheses reflect stronger beliefs than two-sided ones. In hypothesis testing, there are two types of errors we need to be aware of: type 1 error and type 2 error. In type 1 error, also called false positive, we reject the null hypothesis when it is actually true. This is like a false alarm, thinking there's a fire when there isn't one. The probability of making a type 1 error is denoted by alpha. In type 2 error, also called false negative, we fail to reject the null hypothesis when it is actually false. This is like missing the alarm. There's a fire, but we don't realize it. The probability of making a type 2 error is denoted by beta. There's a trade-off between these two errors. Decreasing the probability of a type 1 error increases the probability of a type 2 error, and vice versa. The key is to balance these risks appropriately. For example, if we set a very low significance level, for example 1%, we reduce the chance of a type 1 error but increase the chance of a type 2 error. On the other hand, if we set a higher significance level, for example 10%, We increase the chance of a type 1 error, but reduce the chance of a type 2 error. Now, let's cover some fundamental aspects of hypothesis testing, like testing a single mean, comparing differences between means with independent samples, and comparing differences between means with dependent samples. First up, let's talk about testing a single mean. This is used when we want to determine if the mean of a population equals a specific value. For a single mean, our hypotheses are generally structured as follows. This is the null hypothesis. The population mean equals a specified value, and the alternative hypothesis is that the population mean is different from the specified value based on whether the test is one-tailed or two-tailed. The appropriate test statistic depends on whether the population standard deviation is known. We use z-test when the population standard deviation is known, whereas t-test is used when the population standard deviation is unknown and the sample size is small. Now, let's talk about how we make decisions using our test statistics. When we're testing a hypothesis, we compare our calculated test statistic to a critical value that we get from the z or t distribution table, depending on the significance level we've chosen. For a two-tailed test, if our test statistic falls beyond the critical values in either tail, we reject the null hypothesis. In a right-tailed test, we reject the null if our test statistic is greater than the upper critical value. And in a left-tailed test, we reject the null if our test statistic is less than the lower critical value. So essentially, we're looking at where our test statistic lands in relation to these critical values to decide if we reject the null or not. All right, class, let's dive into testing the differences between means using independent samples, which is handy when comparing the means of two distinct populations. First, let's set up our hypothesis. For independent samples, our null hypothesis is that the means of the two populations are equal. The alternative hypothesis can take a few forms. For a two-tailed test, the means are not equal. For a right-tailed test, the mean of the first population is greater than the mean of the second. And for a left-tailed test, the mean of the first population is less than the mean of the second. We use the t-test for independent samples as our test statistic. This is the formula for the test statistic. Now, for the decision rule, compare the calculated t-value to the critical value from the t-distribution table. In a two-tailed test, we reject the null if the test statistic is beyond the critical values in either tail. In a right-tailed test, we reject the null if the test statistic is greater than the upper critical value. In a left-tailed test, we reject the null if the test statistic is less than the lower critical value. So in essence, we're comparing our test statistic to these critical values to determine whether to reject the null hypothesis. Let's quickly go over how to test the differences between means using dependent samples. This is what we do when we're looking at related groups, like before and after measurements on the same subjects. For dependent samples, we set up our null hypothesis to say that the mean difference between the paired samples is 0. The alternative hypothesis could be one of three things. For a two-tailed test, the mean difference is not 0. For a right-tailed test, the mean difference is greater than 0. And for a left-tailed test, the mean difference is less than 0. We use something called the t-test for paired samples. Here's the formula we use. Now, for the decision rule, we compare our calculated t-value to the critical value from the t-distribution table. For a two-tailed test, if our test statistic is beyond the critical values in either direction, we reject the null hypothesis. For a right-tailed test, we reject the null if our test statistic is greater than the upper critical value. For a left-tailed test, we reject the null if our test statistic is less than the lower critical value. Knowing when and how to use these tests is key to making accurate conclusions in your analysis. Now, let's briefly go over hypothesis testing for a single variance and then comparing two variances. When testing a single variance, our null hypothesis states that the population variance equals a specific value. The alternative hypothesis might state that the variance is not equal to, greater than, or less than that value, depending on whether we're conducting a two-tailed, right-tailed, or left-tailed test. To test this, we use the chi-square statistic. The chi-square value is compared to the critical value from the chi-square distribution table. Remember, as discussed earlier, for a two-tailed test, we reject the null if the chi-square value is beyond the critical values in either tail. For a right-tailed test, if the chi-square value is greater than the upper critical value. And for a left-tailed test, if the chi-square value is less than the lower critical value. Now, for comparing two variances, our hypotheses are similar. The null hypothesis is that the variances of the two populations are equal, while the alternative hypothesis suggests they are not equal, greater, or less. We use the F statistic for this. This F value is compared to the critical value from the F distribution table. Again, for a two-tailed test, we reject the null if the F value is too large or too small. For a right-tailed test, if the F value is greater than the upper critical value. And for a left-tailed test, if the F value is less than the lower critical value. In summary, use the chi-square test to check a single variance and the F test to compare variances between two populations. Lastly, let's touch on the difference between parametric and non-parametric tests. To begin with, let's recall the hypothesis testing procedures we've discussed so far. These procedures typically have two main characteristics. They focus on parameters, and their validity depends on specific assumptions. For example, when we conduct tests concerning the mean or variance of a normal distribution, we are performing parametric tests. Parametric tests are used to make inferences about population parameters, such as the mean and variance. These tests rely on specific assumptions about the distribution of the population. For instance, they often assume that the population follows a normal distribution. Some common examples of parametric tests include t-tests and z-tests. T-tests are used to compare the means of two groups. Z-tests are used when the sample size is large and the population variance is known. On the other hand, non-parametric tests do not focus on population parameters and make minimal assumptions about the population distribution. Non-parametric tests are used when we are concerned with quantities other than parameters or when we cannot assume a specific distribution for the population. These tests are more flexible because they do not rely on strict assumptions about the population distribution. Some common examples of non-parametric tests include Wilcoxon signed rank test and Mann-Whitney U-test. Wilcoxon signed rank test is a non-parametric alternative to the t-test for paired samples. Mann-Whitney U-test is used to compare differences between two independent groups when the assumptions of the t-test are not met. Now, let's discuss when these tests are the more appropriate. Use parametric tests when distributional assumptions are met. If the data is normally distributed and the sample size is sufficiently large, parametric tests are the preferred choice. For example, comparing the average returns of two investment portfolios when the returns are normally distributed. Number two is when the hypothesis concerns specific parameters like the mean or variance. Third is data type, that is, when you have interval or ratio data that meet the assumptions of the test. Great. Now let's switch gears and talk about non-parametric tests. These tests shine in situations where parametric tests might fail or provide unreliable results. Use non-parametric tests if the data does not meet the normality assumption or other parametric test assumptions. When the data is in ranks or uses an ordinal scale, non-parametric tests are appropriate. Third is when hypotheses do not concern parameters. For example, when the hypothesis is about the distribution shape, randomness, or other non-parameter related aspects. Finally, non-parametric tests are more appropriate when the data contains outliers that could heavily influence parametric test results. That brings us to the end of today's lecture on hypothesis testing. Hypothesis testing is a fundamental tool in the CFA curriculum and in the world of finance. It helps us make informed decisions based on sample data and assess the validity of our assumptions. Understanding the steps, types of errors, and the differences between parametric and non-parametric tests is crucial for making sound investment decisions. So keep practicing, stay curious, and remember, hypothesis testing is all about making educated guesses and validating them with data. Happy studying and good luck with your CFA exam preparation.